Good morning. Once again, return to some discussion on the Cantor set. We have already seen that it provides us with excellent examples to suggest certain fine nuances of various aspects of analysis. Now, we have used it or we have discussed it in the context of what are called a Riemann integration. Once again, return to that because we want to fix the notations for doing the work in this case of in the context of Lebesgue measure. So there is some repetition that way. So with these few words, let me welcome you all to Krishna's classroom and start with the discussion of this Cantor set. In this context, there are two basic questions that you discuss. One of them we will settle in this lecture, the other one possibly in the next one or two lectures. If a set has measure 0, is it also countable? Is it necessary? Countable. Now we have seen that if you have countable sets, then the Lebesgue measure of countable subsets of R have measure 0. And we have also seen that every subset of a set of measure 0 is also measurable and is of measure 0. So these two things we already know. So we ask the next question. Is it a characterizing property? That is, the countability, is countability a characterizing property of sets of measure 0? Okay. Or can you say that if a set has measure 0, then it is necessarily countable? This is the question that we want to look at. So in this context, we take up the discussion on Cantor sets. So let us recall. We work I as the interval 0, 1. It's a closed bounded interval. It's a compact interval 0, 1. And now we construct the Cantor set as follows. Remove these. Middle 1/3 of the interval I. Open, I think you need little open interval of length to obtain C1 0 to 1/3 that means we have deleted from the interval 0 to 1. This is 1/3, this is 2/3. We have deleted the open interval 1/3 to 2/3. So this has been, and what remains will be the closed set 0 to 1/3 union 2/3 to 1. We designate it with C1. Now remove 1/3 of the middle 1/3 of each of the intervals and 2/3 to 1 I think. Okay. Obtain C2 3/3 square is 1/3 union 2/3 7/3 square 8/3 square. That is, we have removed the open intervals and seven by 3 square from to obtain C2. So there are 4 closed bounded intervals now in C2. Take each one of them and remove the middle open 1/3 of each of these to obtain C3. Okay, right? Continue this this process, namely removing middle 1/3 of each of the post removing opening those. To get the next thing, namely C3. So we will list out what we have, what comes out of this, which we shall need to use now. So what we obtain is this. Start with I, one closing, C1, which is in fact 0 to 1 by 3 union 2 by 3 to 2 closing. Then we get C3 consisting of 4 closing. Four closing. And C4 provide you with 2 to the power 3 and so on. Ck consists of 2 to the power k so I think I have done here C2, then C3, and this Ck consists of 2 to the power k. Further, and so on. You have I, C1, C2, etc. What we have removed are open subintervals and their unions. So we have essentially removed only open sets. So now we define equal to intersection this is a catalyst. Named after the famous mathematician George Cantor. Okay. Now what we have removed from 1, from I, is a collection of open sets. And hence its complement, which is the is C and is so C is closed. C, okay. So this is one of the properties that observe. The collection CK, K equal to 1 possesses the following properties. One, descending sequence of motions. I, which if you want you can write this as C naught 2 for each k, Ck is the union of 2 to the power k closed intervals closed intervals, each of length that is the setup that you have. You can have a look at by just drawing the diagrams. Now C is called the Cantor set. C which is equal to intersection C is let me just give a word of caution. In the earlier discussions, we have been talking about a more general class of Cantor sets, namely C alpha. And in that case, C1 was used, that is corresponding to the value alpha equal to 1 was used to denote the Cantor set. Okay. So, in this context, we are not taking up the general Cantor set for our discussion, and therefore I think we introduce a completely different notation because we have to go far beyond the structure of the Cantor sets. Okay, so now we can have the following here. Many of the statements are obvious. The Cantor set is a closed, uncountable subset zero one and is measurable with Lebesgue measures. So what we are after is going to the final details of the Cantor set. The Cantor set is a closed set, as we have seen already, because it's the intersection of, it's a countable intersection of closed sets, right? Or it's a complement of an open set 0. So it's closed sets, right? The second part, it says it is uncountable, which we shall prove needs a detailed proof, and then we have to show that it is a measurable set with a Lebesgue measure 0. So that automatically provides you with, once you prove this, once you assert that this is uncountable, it provides us with a uncountable subset of R with Lebesgue measure 0. So that answers our question in the negative. Our question was, is every subset of measure 0 of R countable? The answer is no. So here is an example of a subset of R which is uncountable and at the same time having Lebesgue measure 0. Okay, so let us prove this. Some of them are very basic statements. CKs are used. And C is equal to okay, and is therefore closed. Means a countable intersection of closed sets. Or in fact, arbitrary intersection of closed sets is closed. Okay. Therefore, in particular, countable intersection of closed sets. That proves the first part. A part of the set. Now we observe the following. CK is a disjoint union of 2 to the power k intervals, 2 to the power k closed intervals, each of length 1 upon 3. Therefore, what you have is this. This implies measure of CK equal to 2 to the power k because it's a disjoint unit. So you get this, and that's equal to therefore what happens by monotonicity theorem? Measure of C because C is contained in C. Is CK measurable? Yes. All closed sets are measurable. Okay. Is C measurable? Yes. That's also. Therefore, instead of writing M star, we can write M. Okay. Right. Which implies, and this is true for, and that implies measure of C is that's the proof. So C is measurable and is of measure 0. Okay. So we have proved that C is closed, C is measurable, and C is of measure 0. Now the question is about the countability of C. Now investigate. Let us investigate countability. So is C countable? This is the question that we are asking. So it's a very, very specific question. Okay. Assume. So what we do is we assume that C is countable. Then from the way in which we have constructed C, it would lead to a contradiction. So assume then there exists an enumeration of all elements of C. So if it is countable, then you can write the form Ck, that is C1, C2, etc., Ck, and so on. Okay. Now we try to arrive at a contradiction. So what is that we can say? We can say that you look at the first, see, C1 equal to this is what. So you observe that the element C1 belongs to only one of these two intervals. Or we can say that C1 does not belong to one of these intervals. Call that, denote this by so let us say it is this one, then you denote this by F1. If that is not the case, this is 1 where it doesn't belong to, then you denote this by 1. So F1 is either this or this. Now what one does, Go to the next level. In the next case, what you have is C1 does not belong to F1. Now F1 is a closed interval of length 1/3. So what you are doing is, again you are removing the open middle 1/3 of F1, leaving it as the union of two disjoint closed intervals, each of length 1 by square. In the second stage, remove the open of F1. Then C2 does not belong to one of them. Two closures. Designate this closed subset. So what do you infer? C1 does not belong to F1. C2 does not belong to F2. Okay. So both C1 and C2 does not belong to F2. Now continue this process. From F2 you go to F3. Once again you remove the open middle 1/3 of F2 to obtain F3. Then there are two closed subsets, each of length say 1 by 3 cube, and then look at the status of C3. So C3 cannot be in both of them. So it has to be in one of them. Means it is not there in the other. So the closed interval into which C3 does not fall into, call that F3. Okay. So continue this construction. That is one of the two subintervals of two intervals obtained from Fk minus 1 by removing the middle 1/3. Does not contain Ck. we designate it. So what we have? We have F1 and what you have is that C1, C2, Ck do not now note that one Fk is closed and you have Fk plus 1, okay, 2 Fk is Ck and third property is that Ck does not belong to now what can you say about this? So by nested set theorem, intersection k equal 1 to infinity Fk is smaller. Now this is the important. Okay. So what does this mean? So now what we do is we take, therefore there exists some x belonging to the intersection of Fk's. What do we get? X belonging to okay, and now intersection see that implies x belongs to C. Now since okay, small c is an enumeration of C, x is equal to Cn for This is the crucial argument. Okay. What does this mean? That means Cn equal to x equal to x, which belongs to intersection k equal to 1 to infinity fk, and this is contained in Fn. Okay. So what does it mean? It means Cn belongs to this contradicts. The construction of okay. So Cn cannot be in, that's the conclusion. Okay. Right? And therefore, so that's a contradiction. So the conclusion is that C is not countable. A similar proof can be advanced by taking the ternary expansions of the elements of the Cantor set. Okay, by designating this, so you take 0, 1, then take the middle 1/3. If it belongs to the middle 1/3, then you use the notation 1, 0, 2. So these are the three symbols that we use to represent this. And one gets a ternary expansion for any Cantor set because it cannot belong to the middle 1/3. Successively you do this. Then you divide this. In the middle 1/3 you will be using 1, and therefore a typical will have a ternary expansion etc., where each AI is either 0 or 2. Okay. Now it is quite easy to suppose you have already enumerated all the elements of C, then they are of this form with 2 and 0 appearing in the representation. Okay. So you can construct a new element of C of the same type but different from every one of the ones that you have enumerated. Now you can look at the proof. So I am not going. And that would show that our enumeration is not complete. Okay, which means C is uncountable. Okay. Suppose we have enumerated all elements C. Then each one has a ternary expansion consisting of only 0 and 2. Now what you do is the process is this. X1 is something of the form A1. Suppose X1 is A1, A2, etc. and so on. Suppose A1 is 2. Then what you do is you write a new element Y starting with point. If this is 2, then you write 0. If this is 0, then you write 2. What is the implication? That the element Y that you are defining will be different from X1. And then make sure that Y differs from the second element at the second place in the same way, and so on. So you can construct a Y which is different from each one of these elements of the Cantor set. Which shows that the enumeration is not okay. Therefore, it is uncountable. That is another argument. This is almost similar to this. And compare the two. Okay. So, what we have proved is that thus there exists a uncountable subset of R with Lebesgue measure so C is a closed subset of 0, 1 and is an uncountable set and having Lebesgue measure 0. So that answers our question in the negative. Okay, so we stop our discussion today. Primarily we have only refixed our notation because we shall need it for the next part of the work. Now we are going to take off from here by introducing what is called a Cantor-Lebesgue function. So the theme for the next lecture will be the Cantor-Lebesgue function, which is a fascinating function, some most non-obvious properties. Okay. So as I said in the beginning, that the Cantor set provides us with an excellent example, which keeps within several secrets, and some of these we are going to follow. So, thank you very much.